So now let's take a look at a simple passive filter example for a bandpass filter. And so this circuit probably looks familiar because we've seen it before when we were discussing series resonance back in our frequency response unit. So this is the same circuit, and from that we know that when we were talking about the series resonance, we saw that it had the behavior of a bandpass filter. At the time we said we'll cover this more once we get there, and so now the time has come and we're going to look at the circuit in a little more detail. So just like we did with our previous RL circuit, what we want to do if we're going to analyze our frequency response is to convert this to our frequency domain. So first step is always to take this to our frequency domain, and in doing so what we're going to do is we're going to change our voltages to phasors, and we're going to change our inductance, capacitance, and resistance to impedances. So we have VI and Vout, which are now phasor values. We have our impedance, which is ZL of our inductor is J omega L. The impedance of our capacitor, Z sub C, is equal to negative J over omega C. Note we could also write that as 1 over J omega C. And the impedance of our resistor is simply the resistance value. So that is not dependent on frequency. So what we can do is we could think about doing voltage division. We're going to have the resistor impedance divided by the sum of all three impedances. That's times the input voltage equal to output voltage. So I'm going to go ahead and skip some of those steps and just go directly to writing our transfer function, h of j omega. If you're confused about where this comes from, definitely let me know. We can clear up any confusion. So basically it's just the ratio from that voltage divider equation though. We have R in the numerator divided by the sum of the three in the denominator, so R plus, and then the next two terms have J, so I'm just going to go ahead and factor it out, omega L for the inductor, and minus 1 over omega C for our capacitor. So we get something that looks like that, and again, I'm going to get my numerator 1 just so it's a little more convenient later on, so I can say this is 1, divided by R in the denominator, I have now 1 plus J, times omega L over R minus 1 over omega RC. So we get that expression there. So let me close that to be consistent with the notes. Okay, so let's do what we did last time, and let's look at sort of our general behavior by considering extreme cases. So general behavior from extreme cases. And so again, this is usually a good approach. So let's consider omega equals 0 and omega equals infinity, technically as it's approaching infinity. And so what we see here, so let's first consider our omega equals 0 case. So now we have two locations where we need to consider our omega value. So what we see is for omega equals 0, this first term is going to go to 0, so that disappears, we can ignore that. Our second term, we have the omega which is going to 0 in the denominator, so that means this term is going to be a very large number, so we're going to have negative infinity in the denominator. So 1 divided by negative infinity is of course going to be 0. So we have that our transfer function magnitude of h of j omega is equal to 0. Okay, well, let's look at our other extreme case, and you might see where this is going. So if we have omega equals infinity, so in this case we have 1 divided by infinity, so this whole term is going to go to 0. But here, our omega is in the numerator here, so it's going to be infinity. We then have 1 divided by that infinity, so again, we're going to have 0. So h of j omega equals 0. And so this shouldn't necessarily be surprising to us because we know from the general behavior of the bandpass filter, really low and really high frequencies should be blocked. So it doesn't necessarily confirm that we have a bandpass filter, but it's sort of agreeing with the assumption. So what we need to do then, sort of as an additional step for our bandpass filter, is we can remember we had defined this resonant frequency. So what we can say is at some frequency, and because we've already discussed this, we know we can call this omega naught, we know that we're going to have the magnitude of our h of j omega equal to 1. And so that's basically saying really far on the left, small frequencies, we have 0. Really far on the right, for large frequencies, we have 0. Somewhere in between, there's got to be sort of this sweet spot where our transfer function is 1 and it's passing frequencies through. So again, this happens when our omega naught is our resonant frequency. And so we'll also see that called our center frequency. For reasons that'll be obvious when we look at the plot, it's right in the middle of the plot. And so looking at this general equation up here for the magnitude of our transfer function, so looking right here, we can see that the magnitude of this is going to be 1. And so I've not written that explicitly, but well, let's go ahead and do that. So let's write our magnitude of our transfer function. So oftentimes we can just kind of eyeball our transfer function and not just the magnitude to see that, but let me just go ahead and write that out explicitly. So we're going to have the 1 squared, and then we have plus this quantity of omega L over R minus 1 over omega RC, that whole quantity squared. So the same arguments we had before when we were looking at these extreme cases are going to hold for this magnitude, of course. And so if we are looking for a situation where our magnitude is equal to 1, well, what we say is that this part here needs to be equal to 0. So we want this to be equal to 0 at our resonant frequency. And that just leaves then, of course, our 1 divided by 1 is why we want to do that. So what we can do then is we can say, well, we're going to have at that frequency, of course, frequency is omega naught. So omega naught LR minus 1 over omega naught RC is equal to 0. And if we solve for that, we can solve for our resonant frequency, which will come out to 1 over the square root of LC. And so we'll notice that this is the same equation that we had before when we were talking about frequency response. So the same equation as before. And so it's actually worth noting that all the other equations that we derive for series resonance are relevant here. So all equations from our series resonance notes apply here. And so remember, we had several different forms of all of these equations, but some of the key values were our omega 1, omega 2, our bandwidth B, our quality factor Q, and then of course, as we've already circled above, our resonant frequency omega naught. So the last thing we want to do now is just sketch our ideal response and our actual response. So just sort of overlay the two on the same plot. So we're going to plot the magnitude of h of j omega versus our frequency. Our key values again are going to be 1 for h of j omega and 1 over root 2, which remember is approximately 0.7. We're going to have 3 sort of key frequencies. Our omega naught, which is going to be our center frequency, our omega 1, and our omega 2. And so remember, as we had said before, for our series resonance, omega naught is the geometric mean of omega 1 and omega 2. And so what we have then, let's start with our ideal case. So for our ideal, we said it's 0 until we get to omega 1. At that point, we jump up to 1 and we stay at 1 until we get to omega 2. And then we come back down to 0. So this would be for our ideal case. So for our actual case, what we know, and we haven't gone through and solved this now, but we would have seen this previously when we talked about series resonance, these frequencies omega 1 and omega 2 are where the transfer function magnitude is equal to 1 over root 2. So let me draw a dashed line just to make it clear that these points correspond to where we have that value of 1 over root 2. And we know up here at omega naught that we have 0. And of course, for really small frequencies, we should have 0. For really large frequencies, we should have 0. So what our curve is going to look like is something like this. and we'll be at 1 for a little bit, and then we're coming back down, and we get something that looks like that. And so this is going to be our actual curve for this circuit above. Again, as we make our circuit more complicated, we can improve it and we can make this actual curve a little more similar to what we see for this ideal case. So these corner frequencies, omega 1 and omega 2, just like we've seen with our other types of filters, the difference between the ideal filter and the actual filter response at those corner frequencies is 3 dB. So that's why you also hear those called 3 dB frequencies.